This is the heat challenge activity where you'll divide the class into 8 groups and then divide those groups into 2 parts. One part being the conductor group and one part being the conductor groups, 4 conductor groups and 4 insulator groups. And then to pass out the thermometers first. The thermometers are very interesting just in themselves. It's got 2 scales. Go over the Celsius scale and the Fahrenheit scale. Talk about how much more sense the Celsius scale mean. It just works better with a 0 as a freezing point and 100 as a boiling point. Whereas with Fahrenheit, we got 32 and 212. Who knows what they were thinking? Well, they were thinking about a normal life in England, I think, where 0 is about as cold as it gets and 100 is about as hot as it ever gets. And that's not a very precise way to set up a temperature scale. But anyway, we can look at ours and see that right now here it's 12 degrees Celsius and it's 52 degrees Fahrenheit. Ooh, that's a little chilly. So that's the temperature right now, and then try to make it warm up. You can blow on it. Ooh, went right up past 60, still going up. But if I stop blowing on it, it'll go back down. All right, if you put in a little bit of water and blow on it, it might go down with the evaporation, making it a little bit cooler. You might notice that your thermometer, if your thermometer is not stuck in there well, you can't tell what temperature it is because the thing is wiggling. That's just poor construction because we got cheap thermometers. But ideally, you calibrate this. You go to another thermometer that you know is right, you put it on the right temperature, and then you fasten it down somehow, clamp it or glue it down. So that's a thermometer. That's telling you how hot something is, the temperature of the thing, which is different than the heat of the thing. So what we're doing here is we're going to put hot water into the cup, and then the insulation group is going to try to keep it as hot as possible. Try to keep it from losing the temperature, and the conductor group is going to try to get the temperature to go down as much as possible so that the hot water loses its heat as much as possible. All right, and then each of the 4 groups are going to have different materials. One group is going to have aluminum foil, one group is going to have plastic and bubble wrap, one group's going to have paper. We also use cardboard, but paper's good. And then the 3rd group's going to have styrofoam. And each group's going to have a roll of tape. So you give the group some time to think about how they're going to do it and make a plan and then do it. So they can do it however they want. They could take the paper and wrap it all around it. They could leave it doubled like that. They could puff it up into little crumples if they want. They can rip it into little strips, whatever they want to do. And then, but the cup's got to be in there somewhere, and it's got to be able to pour the water in the top. So if they want to make a lid to it, they got to be able to open the lid to put the water in, and then close the lid again. And then the thermometer's got to go in there at the end to find out how hot it is. And if they have it in there in the middle, well, they can watch the temperature as it goes. Okay, so that's it. You give them 10 minutes to make it, to talk about it, to make a plan, and then to actually put it together. We don't need a beautiful construction with artful fringes on it. We just need to try to keep the temperature the same or to lose the temperature. All right, so they got to do some thinking first. Don't just have them not just go at it. They got to think about what's going to go on here. All right, so then while they're making that, you can draw the table on the board where you're going to put the results, and then you can get their predictions also as they go around. You know, which material is going to be the best insulator? Which material is going to be the best conductor? And write that down, make little tallies on the board so that everybody's got to think about what they think is going to be the right answer. And then at the front, also tell them you're going to have one cup with nothing. It's just going to sit there. All right, nothing at all. And you're going to have another cup that you're gonna have in the front also with nothing at all, and it's gonna have very little amount of water, just a tiny little bit of water. And you can see the difference between having a bunch of water and a little bit of water. So then meanwhile, you've got a little mark on your cup here, and then when you're going to fill their cups, you can fill it up to that mark and then go pour it in the cup. So everybody gets the same amount of water. They may not realize it, but that's a critical thing. If you give one team more water, you're giving them an advantage because you've given them more heat. The more of something there is, then the more total heat there is, even if it's the same temperature. That's the beginning of the concept that the temperature is different from the heat. They're two different sort of quantities. Once you've got it done, then you go around and get there. Oh no! Right after you finish dumping all the water in and you put yours up in front, you get the temperature of your water, and that's going to be sort of the starting temperature. And you can write that on the board, and then you wait 10 minutes. Actually, that's when you can get their predictions. That's when you're going to need to kill 10 minutes because you're just sitting there waiting for the water to cool. That's not one of the more interesting things you can do in life, is to wait for a cup of water to cool down. But here we could talk about what they think the insulative and conductive results of their different constructions are going to be. All right, and then once you got it, then you go around, take the thermometers, and measure it off and get their results, get the final temperature after 10 minutes. And of course, you spent a little time as you poured it into them. So if you take the temperature, if you take the results in the same order, then that kind of cancels that out. And at the very end, you can get the results of your two also, and you put it on the board. So then, if you have time, you can also make the graph. Make a graph with the vertical being the temperature and the horizontal being the bars of each different group. You can see that in the write-up if you have time, if you want to do that. But more important is to talk about how the heat travels, how the heat moves, what is a good conductor and what's a good insulator. You take your data. I mean, this is a real experiment, so you'll take your data and you believe the data. Unless there's something way off, then you look at maybe the thermometer was broken or something, but the data is the data. So then you tell them the theory of how all this stuff works, and then see if it matches your data. So the theory is that to stop heat from flowing, you want to stop conduction from happening. And the way to do that is to make layers of dead space. So for instance, the bubble wrap and the styrofoam, those are excellent insulators because there's all this dead airspace inside there. And so the heat, to travel through there, the heat has to warm up each individual little layer or level of air, and that takes a long time. And the air is not a good conductor, and the plastic is not a good conductor. And so I would assume that these two would be the highest insulative value. The paper also, if you put a bunch of space in it, if you crumple it like this, then there's a bunch of airspace in there, and that's gonna be a good insulator. Aluminum foil is a terrible insulator. It's a conductor. It's one of the best conductors. Aluminum is a metal, and it takes the heat energy right down the line. So it doesn't matter if you're stuck using aluminum, the best you can do is try to make some airspace in there. Try to make some dead air, but still it's gonna conduct a lot faster than paper, in theory. All right. So another key point to keeping the heat in there is to cover it. There's conduction. There's three ways that heat travels. There's conduction, convection, and radiation. Conduction is when it touches something else. When you touch it with your hands, you're conducting that heat to your hands. And when you touch it with the aluminum foil, it conducts the aluminum foil, and then whatever's touching the aluminum foil conducts it away. So that's conduction is actual contact. And when air goes by it, it conducts with the air and gives some of the heat to the air. All right, so then convection is the fact that hot air rises, hot fluids rise in other fluids. So you got heat coming up, heat making the air right above it hot, and then that hot air takes off up, goes screaming up. That's why candles are always pointed upwards, because they heat the air around them and the air takes off up. So if you want to stop conduction, you put a lid on it. That's why you can boil things faster on the stove with a lid. And in this project, if you built a lid, you're going to have much better insulation of your project, of your cup. All right, so that's the insulation side. Now the conducting side, if they thought about it well, you don't want to cover anything with your cup. In fact, you want to raise it up a little bit so there's more air moving around it. So if I was given styrofoam, for example, I think I would take 2 pieces of styrofoam and hold the cup up on top of it. And then I'd take the rest of the styrofoam and I'd blow on it. And then that would make it cool down the fat. That'd make put more air going past that to conduct the heat away from the cup. All right, so the only thing that maybe you could gain would be the aluminum foil, which is an excellent conductor. And then what I would do is I would put like fins on it. I would put fins that like sort of stick out to the side and grab more air. So you can think of a radiator on a car. It's got a big surface area. And so you take it and you make like little wings and fins off to the side of it, and then tape them on there. So now, and don't leave any dead airspace. Make them nice and tight to the side of the cup, like that, and then you'll get better conduction with the air. The aluminum foil will get hot, and then it'll go out. The heat will go out to the edges of the aluminum foil, and then it will conduct away to the outside. But meanwhile, you should also blow on it. You blow on it like this. If you blow on it with your breath, that's okay too, but your breath is a little bit hot. So if you blow on it with the room temperature, it should, in theory, should be even more effective. All right, so then in the end, you check your own cup, which was just bare, and that's sort of the standard. That's what'll happen if you just pour water into a cup. And all the other ones that were different, well, they were different because of whatever the students did with the materials. And then finally, the last cup with only a little bit of water, that one, in theory, that one should go down a lot faster because it didn't have as much total heat. And so it can lose that heat faster. And likewise, if you had a whole big old pot full of water, same temperature, at the end of 10 minutes, that temperature would be a lot hotter, because it had much more heat to get rid of. So even if it was getting rid of heat at the same rate, there was more heat, so it would not go down. The temperature would not go down as much. All right, so that's all about sort of heat capacity. You learn about that in high school, the heat capacity of different things. That's how much heat it can hold. But we don't need to talk about that now, but you do kind of show that if you got a bunch of water, it's gonna stay warmer than if you just got a little bit of water. Okay, I think that's it. As usual, the goal is a discussion, the questions, get the students questions, ask the students the questions, and then try to nail down what you've learned from doing the little project. This is straight from the NGSS. If you do this project, you can check off that one about making a test device that either minimizes or maximizes thermal energy transfer. All right, as well as various other of the science and engineering practices, taking data, sharing data, displaying data, and some of the cross-cutting concepts as well, cause and effect, energy, energy and matter. There's many, many connections to the NGSS here. Right, have fun.